get started by recalling that I defined last time what an asymptotic field is. So it's a valued field with a derivation on it, such that if you have two infinitesimal elements f and g, such that f is strictly dominated by g, if and only if f prime is strictly dominated by g prime. Anyway, then you can associate to such an asymptotic field its asymptotic couple, which is gamma comma psi, where capital gamma is the value group. The valuation is, I'm always indicated the valuation by little v, right? And it's this psi function is defined in the following way. The psi of the valuation of f is the valuation of f dagger. And recall f dagger is the logarithmic derivative of f. In other words, it's f prime divided by f, where you restrict the to f that is not asymptotic to 1. So because you want yeah, right. Because the psi function is only defined initially, at least, for non-zero elements of the value group, although we then extend psi to all of gamma by setting psi 0 equal to infinity, as usual when you are dealing with valuations. Right, so the point is that a lot of the asymptotics of K is visible, so to say, in the value group, in the asymptotic couple, right? And one thing I also want to mention is that the derivation of an asymptotic field is always continuous with respect to the valuation topology. And if your asymptotic field is a Hardy field, which is not contained in R, so that means that the valuation on it is not trivial, then in fact this valuation topology is also the order topology. Right. Okay, so I use the word visible. So then I want to highlight a picture of the asymptotic couple, right? So the x-axis here is the element, the points. You think of the points as elements in gamma, which become bigger and bigger in this direction. Okay, so here is the origin 0, and here it goes to, here they become negative and more negative. And likewise, the y-axis, if you go up, the elements in gamma become very big, and if you go down, they become very small. And now I want to give a kind of rough picture of how you think about the asymptotic couple, about an H asymptotic couple. So this is more, yeah, if I picture, I should perhaps make it a bit more precise. This is really a very symbolic and very rough, it's just written, it's just a picture of, to give you a very rough idea of how to think about an asymptotic couple. But it's more realistic for H asymptotic couples, yeah, of an H asymptotic couple. And even more realistic if you have it's the H asymptotic couple of a Liouville closed Hardy field. Of an H asymptotic couple with small derivation. In other words, the derivation of an infinitesimal is also infinitesimal with small derivation. And okay, so I have so this is how you think of the graph of the psi function. Yeah. As you see, it is psi of minus. It reflects that psi of minus gamma equals psi gamma. It's symmetric with respect to the y-axis, and then right, and then the graph of the identity plus psi, which is, in other words, gamma prime. Yeah, so here I could also think of this as gamma, the graph of gamma dagger, and an alternative notation, and here gamma prime. And gamma prime is simply equal to gamma plus gamma dagger, so that's why here you have the graph of the identity plus gamma. And you can, I've also sort of tried to draw the identity function itself, which is the graph of the identity function itself, which is this line, and you can see, yeah, right. Okay, what else do I want to say more about this picture, because you can read off, I mean, this is a picture that I have almost 24 hours of my of the day in my mind. If I think about Hardy fields or anything related to it. And you can really, if you get used to it, you can just, you get the right intuition, so to say. So you can read off basic features of H asymptotic or of asymptotic couples, or particular H asymptotic couples, such that yeah, note oh yeah, note picture shows many things about such that, like, if you have a positive element in your value group, then its derivative is bigger than all the logarithmic derivatives of positive elements. Yeah, alpha, right, for all beta, for all. Right, I mean, you see there that the graph of the identity plus psi, in other words, the graph of the derivative function on the value group, is bigger than everything indicated on the graph of psi to the, which is to the right of 0. Right, that's right. You can also see in the picture, and yeah, this, I'm also trying to indicate here that the psi function is very slowly varying, but I can't really indicate it fully. Yeah. Yeah. So psi is increasing on the negative part, and decreasing on and slowly varying. In fact, it's very so slowly that it's actually constant on Archimedean classes, but that is impossible to picture. Slowly varying, but in fact, if you have two elements, say alpha and beta, where yeah, I always allow myself to work in the visible hull, so to say, of my value group. So I feel free to use 1/n. So if you have alpha and beta between, if alpha and beta are in the same Archimedean class, that's what this says, then psi alpha equals psi beta. Yeah, and why is that? Well, we know already that psi of n alpha equals psi alpha, and psi, and therefore also psi of 1/n alpha is also psi alpha, and then since psi is decreasing in the weak sense, psi alpha must be psi beta, right? But of course, it's impossible to indicate that in the picture. But impossible to draw, impossible to indicate in picture. We just do the best we can, but right. Another thing, the derivative function on the value group, so to say, is strictly increasing, gamma prime strictly increasing as a function of gamma, well, as long, yeah, things are not defined at 0, so that's why I draw a little circle here. Neither the gamma, well, it's actually, we did define it by setting psi of 0 equal to infinity, but yeah, but certainly gamma prime also is not therefore defined there. Right. So what else do I want to say about this? Yeah, the psi set, capital Psi now, we call this the psi set, is little psi of, is simply the value, the set of the image of the psi function, yeah? Of course, you could also just take the positive part of gamma, or psi of the negative part of gamma, that's the same thing. Right, so the psi set here is well, everything below this here, well, provided is in the image of psi. Yeah, what? Okay, let me see. Did I say? Yeah, right. Yeah, so psi, the psi set, right, is everything that's in the psi set is less than everything that is in the set of derivatives of positive elements, right? If you everything in the psi set is below here, and everything in here, the derivatives of the positive elements, then everything here is above this little dot. So, right. And so you can ask, what about, is there anything in between? And that is a, yeah. Okay, yeah, so we make these definitions for any asymptotic couple whatsoever, although we are mainly interested in H asymptotic couple. Yeah, the reason, you might wonder, why not just restrict your attention to H asymptotic couples? Well, there are interesting situations which have not really been explored yet, where you can start with a differential field of meromorphic functions at some point, yeah, the germs of meromorphic functions at a point in the complex plane, and then analytically continue along some path in the complex plane, and then take the limit, and then consider what happens far away from the point where you start with. Sort of the germs of what you get when you go far away on this path, and then you get a then you often get a differential field which is with evaluation on it, which is which is asymptotic, and where the asymptotic couple is not H-asymptotic, but just asymptotic. So, and a lot of things about that we know about H-asymptotic fields, if you make a little extra effort, you can also prove for asymptotic couples. But nevertheless, that is, in a sense, Hardy fields are kind of like that, right? I mean, at least many Hardy fields, you would start with some point on the real line and take real meromorphic functions defined there, and then analytically extend to the positive real axis, and so you get then a Hardy field. But anyway, I think the notion of an asymptotic couple and an asymptotic field has a lot more in it than just Hardy fields and H fields. Nevertheless, for what we are going to do, we basically restrict our attention to H asymptotic couples. Okay, so yeah, so these definitions are yeah, I didn't actually define what this means, but I think the notation makes it kind of obvious. Gamma is the set of all gamma prime where gamma is positive. Right, and this is true for any H asymptotic couple or even asymptotic couple. Okay, so now I want to mention further basic facts that are okay. Further. Yeah. Well, maybe I should start a new blackboard here. Further basic facts. Again, I refer you to section 9.1 and 9.2 for proofs of this, but I will mention a few things that are not in. I mean, some of the basic facts were proved by Rosenlicht, but I will mention a few that are not there that we found out. Further basic facts about asymptotic couples in general. First of all, if you take the things that are not derivatives of elements in gamma, that there is only one element that there can be only one such thing, has at most one element. Most one element. Well, you can sort of see that in the picture. Yeah, the gamma primes seem to take all values here, except maybe something that corresponds to this little hole there. Right, and that is a realistic statement. You can prove this, although the proof is not that, is a little tricky. And moreover, and equals the maximum of psi equals the maximum of the psi set if there is a maximum, if psi has a maximum as the largest element. Well, and then as a corollary, let me see. Yeah, just to be on this. Okay, so this is still for arbitrary asymptotic couples. The corollary, in my notes, I say There is a, yeah, no, this is still correct even for arbitrary asymptotic couples. There is at most one beta, there is at most, that lies between capital Psi and there is at most one beta such that capital Psi less than beta less than gamma prime. Right, so everything that must be a beta that is bigger than all the things here and less than everything there. So it should correspond to this whole. Right, because if there were two betas, yes, if there were two betas, then they couldn't be derivatives of non-zero elements, because if it were the derivative of a positive element, it would have to be in here, and if it were the derivative of a negative element, well, then it would have to be below one of those things, and so less than something in Psi. Right. Okay. Yes. Right. Good. Yeah. Now, so such betas are very interesting. We call them a gap. So
là-haut,
yes,
yes, Jean-Philippe Rollin. If the set psi, big psi, has the largest element,
yes.
in that case, does there exist such a beta or not?
No.
No. Okay.
I should say that there is at most one beta such that cannot occur if C has a largest element.
Okay, thank you.
Right. Right. Okay, so now I want to introduce some terminology to because this leads to a kind of trichotomy in okay, such a beta is called a gap. A gap in our asymptotic couple, gamma Psi. And so there can be at most one gap. And these gaps are extremely, well, significant, so to say, but it's not so easy to get them, except in, well, okay, maybe I should also say, if it is a gap, then it remains a gap if you go to the divisible hull. Yeah? It remains a gap, in, I already, when you take a real closure of a Hardy field, for example, or algebraic closure of an asymptotic field in general, your value group becomes the divisible hull of the original value group. But a gap remains a gap. Terminology. Right. Yeah. Okay, this is already part of the terminology, but further terminology. We call gamma psi grounded if the psi set has the largest elements. The psi set has the largest elements. And we say that gamma psi has asymptotic integration. And I will give examples as asymptotic integration. If every element is a derivative in other words, gamma is every element in gamma. Yeah, note here I said that gamma can have at most one element outside this. If there is no such thing outside, then we say that gamma has asymptotic integration, right? The reason, well, if everything is the derivative of something, then that means basically you can integrate. Of course, here integration is pure in the asymptotic couple sense, right? And it doesn't mean that if you have an asymptotic field whose asymptotic couple has asymptotic integration, that you can, that every element in the field has an antiderivative. It only means that every element in the field is so to say close to some derivative. Well, and even that you have to be a little bit, yeah, anyway, that's the definition. And now we have the following trichotomy, which is but this is for here we really restrict. All these definitions still make sense for ordinary asymptotic couples, but I think from now on, let's just consider H asymptotic couples. Yeah, for H asymptotic. Yeah, exactly one of the following three how happens. Exactly one of the following. Well, one, you have a gap. Gamma psi has a gap. Well, two, you have a largest element, in other words, grounded, gamma psi grounded. And I will. And the third is that you have asymptotic integration. Gamma psi has asymptotic integration. I mean, this was already suggested in the papers by Rosenlich, but he didn't quite prove it. Right. Okay. Yeah. Right. And okay. Yes.
Can you start with any of these and expand the H field and then get to any other?
Yes.
By adding enlarging the field, you can move from anyone to anyone?
Yeah, yes. I want to say that is definitely the case. But let me give basic examples. I mean, the easiest, in some sense, the easiest one is part one, if you just allow gamma to be trivial, right? So, yeah, if for gamma, the trivial group, Well, the psi function is then is not defined. It has empty domain. It's defined, of course, but its domain is empty, and the psi set is therefore empty, and this is also empty, right? This is empty, and this is empty. So there is a gap, namely 0. Yeah. This means beta is bigger than everything in here and less than everything in there. But if both of these, this set and that set, are empty, then that means that 0 is really a gap. Yeah. For gamma 0, psi is gamma empty, so 0 is a gap, and this is not a joke. It really does, right? But and it's not trivial to come up with other asymptotic couples with have a gap. Yeah, not trivial. Not trivial to construct other H asymptotic couples. With a gap, it's certainly possible, and also it can be realized. These asymptotic couples, there are Hardy fields strictly containing the reals, whose asymptotic couple has a gap, and so and not strictly extending the reals means in particular that the gamma is not trivial. So these things do exist, but to construct such Hardy fields is again a non-trivial thing. I'm not sure even if Rosenlicht was had examples of. I'm not sure if Rosenlicht had examples of that, but anyway, right. So, okay, the second case, grounded. Well, this will happen if, for example, if the gamma has finite rank. Gamma not trivial. Yeah. So 1, 2. Suppose. Well, let's say gamma is gamma is simply finitely generated abelian group. Suppose gamma is finitely generated. As an abelian group, or more generally, if its rational rank is more generally rational rank is finite. Yeah, this means that if you go to the divisible hull, so that it becomes a vector space over Q, that its vector space dimension over Q is finite. Oh, and of course not trivial, otherwise you would be in that case. Then gamma psi is grounded. Well, for the very simple reason, because then the psi set is finite, then gamma psi is grounded, since the psi set has a, well, in fact, I think that the psi set has at most as many elements as the rank. Yeah, since then, now the psi set is less than or equal to this rank. Right. Actually, even the rational rank you can replace by the Archimedean rank, so to say, the number of Archimedean classes. Yeah, I already mentioned for an H asymptotic couple, the psi function is constant on Archimedean classes. So if there are only finitely many Archimedean classes, which is certainly the case in when the rational rank is finite, then the psi set has at most, there are at most as many elements in the psi set as there are Archimedean classes. So right. So this is rather clear, right? And 3 is, for 3 is, for example, the case when you have a Liouville closed Hardy field. If H is a Liouville closed Hardy field, well, or more generally, a Hardy field which is closed under integration, right? Every element in the Hardy field has an antiderivative in it. Well, then its asymptotic couple is asymptotic, has asymptotic integration, yeah, or more generally. If H integration closed, H is H prime equals H. Yeah, that's one way to express it. Every element in H is the derivative of something in H. Then let's see, as asymptotic integration. Yeah. I think this is also makes perfect sense, but you can see that you need some kind of infinite construction, right? If you just start with Hardy fields generated by finitely many elements, and these elements are differentially algebraic, then your value group will satisfy this condition, and so the psi set will be finite, and therefore the thing will be grounded. But so in order to get to something with asymptotic integration, you have to have something like this, an infinite construction, an infinite as asymptotic integration. Right. Okay. So yeah. So this is a trichotomy that one always has to keep in mind. But yes, it is possible always to go from a grounded one to one with asymptotic integration, to extend to one that has asymptotic integration, and also to go from one with a gap to one that is grounded, to extend to one that's grounded, to go from one with asymptotic integration to one with a gap. That is a bit trickier, but it can also be done. And these extension procedures are actually quite important in the. There is a good model theory for these H asymptotic couples, which I will say something about. If I can find my notes. Let's see. Right. Oh yeah, but the Liouville closed case, I want to say more about the Liouville closed case, because yeah. Right. In the Liouville closed case, the psi set is actually downward closed. Right. So for Liouville closed H, Liouville closed Hardy field H, the psi set C is downward closed. So that means basically that is because every element in a Liouville closed field is also the logarithmic derivative of something, not just the derivative of something in it, but also the logarithmic derivative of something in it. And so there are yes, downward closed. And so this makes the picture, this picture is still more realistic for a Liouville closed H field, because in this picture I did draw the graph of psi in such a way that it suggests you know, that there are no gaps, that there are no interruptions in the graph, like a continuous function. But of course, that is not a good picture if you are dealing with, for example, a grounded with something like this, where the psi set has only finitely many elements. But in the case of a Liouville closed H field, you everything, all the things below this, yeah. So in the image of the psi function are in the psi set, and also it means that the graph, although the psi function is very slowly varying, extremely slowly, it goes all the way down. It's yeah. Right. Okay, so now I can actually state a model theoretic fact. Yeah, let's say consider. Oh yeah, still, I didn't explain here the notation. Here I indicated a positive element in the value group, which I call 1, and which in the case of a Liouville closed Hardy field would be the valuation of 1 over x, yeah, x being the usual element with derivative 1. And minus 1, yeah, minus 1 is the valuation of x. That yeah, so maybe I should say a little bit about that first. Yeah, maybe I should say something about that. So if the psi set has a positive element, if the psi set has a positive element, and that's the picture there, intersected with gamma not empty, then certainly you have small derivation. Then we have small derivation. Yeah. Then we have small derivation, i.e. alpha positive implies alpha prime positive, which again is visible in the picture. But even more, there is a unique positive element which is fixed by psi. Yeah? And that is a unique positive element. Fixed point of the psi function. And yeah, there are good reasons to call that, it's a kind of a natural unit of length, and to call that 1, yeah, which of psi, which we call which we call 1, right? So that is what this 1 here is. It's a fixed point of the psi function. You see, this gap is just a little above this. This little hole is just a little bit above 1. Right, but you see that this is the fixed. Here you have a fixed point of the psi function. Right, and in a Liouville closed H field, this 1 is actually the valuation of 1 over x, and -1 is the valuation of x. Right, if you take x. If you take the logarithmic derivative of 1 over x, what do you get? It's minus the logarithmic derivative of x, which is, and the logarithmic derivative of x is 1 over x, so you get minus x inverse. Right, but of course the minus sign doesn't make any difference for the valuation. So the valuation of this thing is the psi of the valuation of this thing, and so, and since x and 1 over x and minus 1 over x have the same valuation, that means that you do have a fixed point there. And this is also right. So now I can state a theorem about that Matthias and I proved way back, but yeah. So consider normalized H asymptotic couples. Normalized because I add a distinguished element 1 with 1 positive, with 1 greater than 0, and C1 equals 1. In other words, you simply give a name to this fixed point. And you also restrict then to the case where the psi set has a positive element automatically. Okay, then we have the following theorem. Okay. The theory, I mean, this is of course a first order notion, right? If you have a language for normalized H asymptotic couples, you have, because you have, this is just an ordered abelian group, you have a function on gamma. Well, you have to make some convention about psi0, but that's not too important. And you have a distinguished element 1 with satisfying this, and so this is so to say a universal theory of structures. And okay, so gamma C1 is existentially closed in this category of normalized H asymptotic couples, if and only if three things happen. One, well, yeah, so here I'm in a class of normalized H asymptotic couples. Yeah, okay, so here I'm using this notion that I'm not sure everyone is familiar with, but it means that every existential sentence with parameters from gamma, which is true in some extension, in some normalized asymptotic couple that extends this, is already true here. So it's like algebraically closed, or anyway. First of all, gamma has to be divisible. In other words, every gamma equals q gamma. Every element is n times something for every positive integer n. Secondly, you have asymptotic integration. Gamma psi has asymptotic integration. And 3, the psi set is downward closed. Is downward closed. Right. And so in other words, for those who are familiar with this, this notion, the theory of normalized H-asymptotic couples has a model companion, and the models of the model companion are the ones that satisfies these 3 conditions. Yeah. So let me say that here. The theory of normalized asymptotic. So this was, yeah, when did we do that? Matthias and I, we did this in the it's hard to think back so long ago. It's still in in the 20th century, 2098 or something like that. The theory of normalized asymptotic couples as a model companion. Whose models are the ones that satisfy these extra conditions, and so and you will even have quantifier elimination once you add a predicate for the psi set. Yeah, and it has QE quantifier elimination after adding. But you really need to do that. You do not have QE without adding a predicate for psi, after adding a predicate for psi. Yeah, it's even, wait a minute, I have to be very careful here. Yes, in this language, it's even weakly or minimal, and we even gave a proof of that, but we found out later, only a year or so ago, that there is a gap in the proof. Not in the proof of this fact, but in the Vico minimality, there is still a little gap that we are now, we are revisiting asymptotic couples, and we found out, first of all, we had this paper about this that is like 60 pages, and where we do a lot of other things like what you say, Vico minimality. But we did find there are some things there that are not 100% proved. So we are revisiting this now and give some simpler arguments, and also adding a full proof for the Vico minimality. Right. Yeah, and this is sort of a baby version for our for the extension theory of H fields. That and also a lot of the phenomena that you encounter here are you encounter in a much more complicated way when you are dealing with the field setting. Okay, so let me see the. I think I want to say a bit more about even the Liouville closed case, because there is something extra beyond. You see, okay, example, I want to consider the Liouville closed. Suppose H is a Liouville closed Hardy field. Well, I always say Hardy field, but in fact, a lot of what I say works in a much more general setting of H fields, which is a first order notion. But Hardy fields are sort of more concrete and more intuitive. Hardy fields. And for, well, just let's assume for simplicity that it contains the reals, which of course you can always. Okay, then you have it normalized. Then it's normalized. It's normalized H asymptotic couple. Gamma psi 1, where 1 is now the valuation of 1 over x. I wanted to say closed because it's existentially closed. So it's a model of this. Yeah, this theory is also. Yeah, I should also say it's a complete theory. A theory, and it has which is complete, complete theory, and has QE after adding a predicate for the psi set. Right. So these are natural. You can see that these things are not just artificial objects constructed just to satisfy model theoretic desires, but they arise here naturally as H asymptotic couples of Liouville closed Hardy fields. And but here there's more structure on the value group than what we specified there. But in this case, gamma is naturally a vector space, not just over Q because it's divisible, but over R. In this case, gamma is naturally a vector space. Vector space over R. And how is that? Well, we simply say R alpha is the valuation of f to the power r, where for, let's say, f in H positive and r is a real number, right? Valuation f is equals alpha. So if you take any element in positive element in H that has valuation alpha and raise it to the power r, which of course is possible in a Liouville closed Hardy field, then the valuation of that is then R alpha defined this way does not depend on the choice of f and does not depend on the particular choice of f. So this is a well-defined operation, and it makes it a vector space over R, which extends, of course, the usual Q vector space structure. And in fact, the above quantifier elimination actually goes through when you view this as a two-sorted structure, where R is the extra sort or the underlying set for the extra sort, and you have the ordered field structure on R and the scalar multiplication operation as your extra operation. So you then, yeah, so QE results goes through and again this plays a role in certain contexts for the two-sorted structure. For the two-sorted gamma C1, let's say gamma R C1, and then the scalar multiplication. Right, so now we have gamma as an ordered abelian group, R as an ordered field, and then the psi function on gamma, the one distinguished element of gamma, and the scalar multiplication relating the two sorts. Right, so you have, of course, when you talk about two-sorted structure, you have two kinds of variables, one ranging over the element of gamma and the other over the real numbers. Right. And I also want to say that this two-sorted thing naturally lives in H. It's interpretable in the differential fields. Yeah.
R is the residence field? R is just the residence field?
R is also, yeah, because I'm assuming that H contains all the real numbers. This is also that it's the constant field as well as the residue field, right? Yes, example, yeah, it's interpretable for those who interpretable in H. You can think of this as living somehow naturally in H. You can completely reconstruct it from H as a in H as in the differential field, H. Why is that? Well, first of all, since H is Liouville closed, the ordering is already definable, and then the valuation is definable as the things that are the valuation ring is definable as the things that are bounded in absolute value by a constant. The constants are exactly the real numbers. So R, you have R available, and then the valuation is there, is interpretable there, and then the scalar multiplication. Well, here you have to be a little bit careful because f to the power r is not a definable operation but you could also alternatively, yeah, or R alpha equals beta, if and only if there are Fg in H such that valuation of alpha, so that alpha is the valuation of F, beta is the valuation of G, and RF dagger equals G dagger. Right. So you see, in this way you describe the scalar multiplication purely in terms of definable operations, without talking about powers. Of course, f to the power r is an element whose logarithmic derivative is r times the logarithmic derivative of f. So, right. Yeah. So now I want to go to another short section. Yeah, so the asymptotic couple of a Hardy field reflects only part of the asymptotics, but it so to say, it reflects the more visible parts. You can sort of visualize the asymptotics of your Hardy field in terms of its asymptotic couple and thinking of this picture all the time, which we do. Yeah, after all, you can see there is a lot more to Hardy fields than just asymptotic couples, because Liouville closed Hardy fields are from the model theoretic point of view still very primitive. You can only basically they only allow you to solve first order linear differential equations, which are plus, of course, it's also real close, so you can also solve algebraic equations, but from the but they are still from the model theoretic point of view very small things compared to what you really want to understand, and so there is more to the asymptotics than just these asymptotic couples. Okay, so I want to, so one more step I want to take is I want to talk about cuts in Hardy fields. And again, this is a section just like the previous one, where I'm just going to just phenomenology. Yeah. This seems to be a standard term in physics. I'm just mentioning phenomena that happen and which you have to be aware of and which take really a effort to get used to, for us at least. Yeah, so of course extending Hardy fields, which is really what we have been aiming for all the time, means realizing extending a Hardy field H means realizing cuts, means in particular realizing cuts in H. And now we are actually going to focus on cuts in the positive part of H, yeah, for convenience. Is not really loss of generality at all, but for convenience we focus on cuts in the positive part of H. And such a cut is then simply identified with its a downward closed subset, yeah, and such a cut. So any downward closed subset in this set of positive elements we call a cut. Such a downward, such a cut is identified with with a downward closed. Cuts are simply downward closed subsets of its bigger closed subset of H. And there are 5 that are particularly important to understand. Yeah. Since I cannot move this blackboard, I think it's better to work on one of the other ones. Right. So there are 5 cuts plus infinity, L infinity, gamma, underlined, bold gamma, so to say, lambda, and omega, bold lambda and bold omega. And that makes sense in any Hardy field, or even in any H field that I want to talk about. Right, of course they depend on H, so you should in principle put a subscript H there, but I'm not going to do that. So what is plus infinity is the easiest one. This is simply H itself, yeah? Or H, this is H greater. This is all of H, positive part of H. So a realization is simply an element that is bigger than, is an H-Hardian element that is bigger than H. Yeah? So a realization of plus infinity is an H-Hardian. That means an element in a Hardy field extension of H, which is bigger than everything in H. So now this is very visible in the, where are the, how can you, what does this correspond to in the value group? Well, if you have infinite elements in H, then that means the more negative you get in the value group, the bigger the elements become in absolute value. Plus infinity means in H means minus infinity, so to say, in the value group, right? So it's all, yeah, it's just infinitely far in that direction, in that direction. Right. So this is fairly easy to deal with, although even that takes some effort. Yeah, L infinity. L infinity. This is right. This is the valuation ring, the positive part of the valuation ring. Yeah. Right. Yeah, this is the valuation ring, so everything that is bounded, but then only the positive elements there. And so what is the realization? So a realization of L infinity, and I'm going to explain why we call it L infinity, is an H-Hardian Y such that, well, it has to be bigger than everything in here, which means it's bigger than every real number, and it has to be smaller than all the things that are bigger than that. So in other words, it is an element that is bigger than every real number, but smaller than everything in H bigger than R. So these are the elements in capital H that are bigger than every real number, and so, yeah. What does this correspond to in the value group? Well, we are still talking about infinitely large elements, so they are on this side of, they are on the left side here, but evaluation 0 means bounded, right? So, but if you get closer and closer to the origin there, then you right. So it's basically yeah, it's the cut that's here. That's where L infinity lies. Right. And why do we call it L infinity? Well, because, right. So you think of such Y as a small positive infinite element. It sounds contradictory. Yeah? Positive infinite suggests very large, but it's as small as possible when you restrict to infinitely large elements, right? Infinitely large because it's bigger than all the real numbers, but as smaller than everything that is already positive infinite in H itself. It's a small positive infinite element. So typical things like that are iterated logs. Log is positive infinite, but you know, but the more you iterate log, the smaller you get, although still staying positive infinite, right? So the notation L infinity is to suggest a kind of infinitely iterated log, kind of infinitely iterated logarithm of x, logarithm of x, right. And more precisely for h, if you take for h, let's say the Liouville closure of the reals, right? So the smallest Hardy field that contains the reals and is closed under antiderivatives and exponentiation. And in particular, it contains x itself. We have, so all the logarithms, all the iterated logarithms of x lie in here. We have ln given by ln in h given by L0 equals x, L1 and ln plus 1 is log of ln, right? So L1 is log x, L2 is log x, etc. And these are co-initial. Ln decreases, but they are, yeah, and okay. It's a strictly decreasing sequence of positive infinite elements, and so a realization of this L infinity is simply something that is smaller than every Ln, but is still infinite. Yeah, so it's co-initial in H bigger than R. And so realization of L infinity is an element, is an H Hardian Y such that, well, it's less than all the LNs for all n. And that is the reason why we think of this as a sort of an infinitely iterated log. Right. And where, yeah, okay. So I already indicated it's somewhere just to the left of the origin, but bigger than all the things here. That's in, right. So these are still visible in the value group. These, and the next one, gamma, is still visible in the value group. But after that, we get two cuts that are not visible in the value group at all. Let me see what. Where are we? Oh yeah, I still have. I'm supposed to stop at 10 to 11, right? Okay, yeah. I still have, right. Yeah, right. Okay, so now the gamma, right? So I have these 5 cuts there. I talked about plus infinity and L infinity. Now gamma, it's sort of like the gap in an asymptotic couple, but the cut gamma is the cut gamma is determined by requiring for H, for positive H, following H, when you view the cut as a downward closed subset of H, of the positive part of H, if and only if the integral, it has a finite, yeah, the integral from some point on to plus infinity of H is finite. Yeah, so this is a very symbolic notation, but take a realization of H, sorry, take a, not a realization, a representative of H as a continuous function, and then integrate this continuous function from some starting point A, yeah, to plus infinity. So fully written, you might write H as ds. But you see, whether this happens or not does not depend on which continuous representative H you take, and nor does it depend on the initial point from where you start to integrate. So, why not just write this? Right. Of course, you could also simply say it's less than let me see. Yeah, it's less than every derivative of an infinitely positive for all G that are positive infinite. Right. Okay. Yeah, which of course is the same you see, if you want to indicate the connection to the previous, all these gaps are related. Sorry. No, L infinity is a special, sorry, plus infinity is a special case. It's not really related to the other gap, but all the other gaps, plus L infinity, gamma, lambda, and omega are closely related, so to say. So you could also say this is bigger than L infinity. H. Of course, this is just a suggestive notation, but I think it makes right. Oh, and what is the a realization of this? What is it? It's an H-Hardian Y. It's an H-Hardian Y greater than 0, such that, well, it falls exactly between capital Psi, and it's like a gap, except that it might lie in a bigger asymptotic couple. Gamma, right? It's sort of, yeah. And again, for the case of, I always have this example of the Liouville closure of R in mind. Yeah, now I have to, maybe I'll write the rest about gamma here. Yeah, so again, to make this more intuitive, I hope, for H is the Liouville closure of R. we have certain, yeah, for H the Liouville closure of R, we introduce these iterated logarithms, right? And if you take their daggers, you get we have elements gamma n, which is, let me see, I have to be careful because it's very easy to make a mistake with signs. So no, this is Ln dagger, which is equal to, and that is L0, L1 up to Ln. If you take the dagger of Ln, well, it turns out to be important to know this. It's 1 over L0 up to Ln. And what is the realization? So a realization with, okay, so these are in the cut. These are elements in the cut, and they are cofinal. Yeah? And gamma n strictly increasing. No, wait, yeah, wait a minute. What am I saying? It's strictly decreasing, right? Yeah. So the bigger n, the smaller this becomes. So they are strictly decreasing. Right. Hmm? No, this is, I'm going to, that will also come up, but not here yet. With gamma n strictly decreasing and co-initial in well, H bigger, the things that are bigger than gamma. Certainly they are decreasing, right? And a realization of this gap is gamma is an H-Hardian Y, such that, well, it has to be smaller than everything here, but bigger than, and here I think ln minus 1, but now instead of ln, you put here ln squared. Maybe that is what you, oh, maybe this is not visible anymore. Is it too low? Can you still read it? But just to, let me go to another blackboard too. Oh yeah, wait. The one that's so a realization is one that has to be smaller than all these things, but bigger than all the things where you, instead of ln here, you have ln squared. But
How can they can't be smaller? No? The gamma should be above. The realizations of gamma should be above elements in gamma. No?
What am I saying? They are strictly, wait a minute, are these gamma n's? Ah, wait a minute, they are bigger than gamma. Sorry, these are bigger than gamma. They are bigger than gamma, but they are strictly decreasing and co-initial in everything that's bigger than gamma. Yeah, it's very easy to make mistakes here. So a realization of gamma is an Ace-Hardian Y such that it's L0 up to Ln minus 1, and now you write Ln squared here, less than Y, less than 1 over L0 up to Ln. Yeah? Or you could also, in other words, it's bigger than 1 over Ln times gamma n for all n, and it's less than gamma n for all n. Right, now it makes sense, I think.
What is gamma n? What is gamma n?
Gamma n, didn't I define gamma n?
Yeah.
Gamma n is 1 over L0 up to Ln. And right, yes. Do you agree now?
Yes.
Oh, okay. Yeah, I think you had in mind that yes, but again, I was a bit confused about bigger and less than, bigger than gamma, and yes. Right. Okay, so let me, okay, but it's still kind of visible in the value group because in the asymptotic couple, because a realization will be just something that is in this little hole there, right? If you view the vertical axis as your gamma. So yeah, so here you have these ln's, here you have these ln's, and here you have the ln daggers, which is gamma n. Again, I should really write the valuation of Ln. Here are the valuations of the Ln. Here are, and then if you go in this direction, the valuation, and then take the daggers, you get closer and closer to there. Yes.
I think we read the daggers of this curve. The dagger.
Well, no, this whole curve is the dagger, the graph of the dagger function. So it is more convenient to work on the negative part here, because then the function, the dagger function. Oh yeah, I see what you're. Yeah, you're right. The daggers lie, yeah, as the valuations of the Ln approach zero, the daggers of them become closer and closer in to here. Yeah, that's what you, and you're right. I was confusing the
Realization of gamma, the derivative of a realization of L infinity?
say again.
Is a realization of gamma, is it the same as taking the derivative of the realization of L infinity?
Yeah, I think so. Yeah. In fact, yeah, this is a good way to think about it. But at the same time, you could also think of it as the dagger of something in well, actually about in Hardy field you have to be careful. In H field it can be realized in two ways as a dagger of something in gamma and as the derivative of something in gamma. It's either way is possible, but in Hardy fields, of course, the situation is completely fixed by what the yeah. Okay. I want to finish with an open problem. Yeah. Okay. Let me also say we think of gamma. Think of gamma as 1 over L0, L1, L2, as the inverse of as this product. Yeah, 1 over this infinite product. Which of course is just a suggestive way of thinking about it. That's all it is. But you see, it's still kind of visible, this gap in the value group, because it's like this dot here, or this little open circle. Right. So, and a while ago I was trying to solve certain problems about Hardy fields, and I couldn't, because I couldn't solve some very basic question. I couldn't answer a very basic question about this gap. So I want to pose this because it might have an easy answer or not. I have no idea. So open problem related to gamma. Suppose I already mentioned in my how do you call it, workshop lectures. Suppose Fg are Hardian. Hardian. I guess Hardian. And positive, just to be. And suppose the integral of f is finite, and the integral of g is infinite. Right? So you can think of yeah, right. So this means if f is in a Hardy field H, that f is in the downward closed subset gamma bar, and if G is in a Hardy field, this means that G is in the is bigger than this gamma in its Hardy field. Now the question is, does it follow that f is? Does it follow? Do we always have? Do we always have that f is strictly dominated by G? I would really like to know the answer to that. Now this is The answer is certainly positive if they lie in the same Hardy field. Yeah. Yes, if Fg in the same Hardy field. Yeah. But so the right, because then the value, then it simply means that the valuation of F is bigger than the valuation of G, since well, these valuations are valuation of F must be below this thing here. The valuation of G must be, oh no, it's the other way around. The valuation of F must be here, and the valuation of G is there, and so right. Yeah, so I mean, of course, one way to answer this is to show that F and G for such Hardian elements do lie in the same Hardy field. In other words, does it follow that F and G, that there is a Hardy field that contains both F and G? That's, even that is conceivable, but sounds a bit too optimistic, but this is a weaker question. And since F and G are extremely regular in growth, right? F has to, this means F decreases rather very regularly and very yeah. And G, of course, doesn't have to decrease, but it's hard to imagine that this could not be true. But the Hardian assumption here is, of course, essential. I mean, this would certainly be false if you just assume that F and G are continuous jumps.
Would be Hardian, the G tree with the
Yeah, Hardian means they live in a Hardy field. They are elements in a Hardy field. Right.
The question is whether they are comparable at all.
Yeah, right. It's actually enough, yeah, enough to show that, enough, if you like, to show that Ft is less than or equal to Gt eventually, yeah, if you take representatives of these germs, because once you can show that, then of course you can always replace F here by n times F, right? The integral of F is finite if and only if the integral of n times F is finite. So if you can prove this for any such F and G, then you can replace n by F by nF, and then you get this. But so could it possibly be that G, though its integral is infinite, dips infinitely often below, if this is F with a finite integral, could it possibly be that G will dip infinitely often below G, or infinitely far away? For arbitrary large t, Gt will be less than Ft. It's hard to imagine. I mean, F and G both have to grow in a regular way. So how could it possibly be that this is not the case? But that's of course not a proof. Far from it. Okay, I'll stop here. And the other cuts, which are really not visible in the value group, but are very crucial, I will talk about on Tuesday. And then we will stop for okay.
And then there's a question section. Yeah, so we'll take a 15-minute break, and then there will be a question session for Lau, which will be held here, but also available for people on Zoom.
Right.
So I'll be upstairs on Zoom to coordinate things,
Okay.
how it works.
Right. Okay. Oh, I guess I don't need this room.